So why are we focusing on this idea of using indirect operands? Well, actually, there are multiple reasons. Let's consider using a pointer variable in the C program. So for an example, we could have integer pointer ptr value equals address of value. Right, so we already have an integer right here. This is like an integer in memory. Now we want to have ptr value, so we're just going to duplicate this because the pointer is going to have the same size as integer on 32-bit. So I'm just going to adjust this. So this is now ptr value. So let's try this example, sort of like how it would look like in our assembly code. So what we could do here, we could say move into a register. Again, I'm just picking EAX, offset of value, and then we can store this in ptr value right here. You can store this in ptr value and store this register now, and let's add comments. So the first line, what it does, it basically sets EAX equals address of value. That's what is happening right here. And then of course we just set ptr value equals EAX. Right? So that's the idea. So this would be the idea that we are able to take address of the variable, we have to load it into the register, and then we can store it in the pointer. So later we have to be able to dereference a pointer. Okay, so that would be another step. What do we need to do? Supposedly, like, take this pointer and dereference it and set the memory location equals 5. So what we would do here is, of course, we would load, again, I'll just use the same register, load this pointer value into a register, and then right here we just use move instruction, move EAX five. So let's add again, like pseudocode comments. So EAX, in our case, we already know that we have stored their address of value, which is an integer, and here what we're trying to do is essentially dereference this address EAX. This is what the square brackets do in our assembly code, dereference this value and set it equal to 5. So clearly we have to use this syntax, we have to use this indirect operand to implement pointer indirection, or also known as dereference operator in C. But in C, pointers automatically remember the data type they're pointing to. In case of a register, CPU of course doesn't know, and assembler doesn't know, so we have to explicitly say that this is double word pointer. Okay, so we need to specify that this register contains an address or is a pointer to a double word, which it is, which is here. So we're going to be updating this value with 5. Okay, so let's just make sure that all of our syntax is correct. I'm just going to hit build, and it builds okay. So you should already know that pointer variables in C have very close relationships with arrays. So for dynamic indexing of array elements, including indexing of multidimensional arrays, those things also require use of instructions with indirect operands. So for example, if we have something like an array of characters, so let's try this too. So supposedly we have some kind of, again, this is an example from C programming language. So we have an array of characters named bytes. We would like to have 5 characters in that memory, and we'd like to initialize them all with 0. You know that this short initializer list will populate all of these bytes with 0 value. Okay. So, of course, it's pretty simple in terms of defining another, let me actually split the screen to keep everything visible. So this is the part of code that we're trying to work on right now. And we can add this array of bytes. I name them bytes. Of course, the type is byte. And we're going to have 5 duplications of 0. Duplications of 0. Okay, so this is how the array declaration would look like here in our global data segment. So then let's try something like essentially we want to update a specific array element with the specific value. What we can do, so first we can move into register EAX just the offset, right? Again, offset of bytes, and then we can, for instance, let's update the third element in this array. So the third element will have index 0, 1, 2, because arrays are 0 based in C. So our index, we can use EDI, which is a destination index, and we can preload it with 2. And what we can do then is we can move into address that would be combined of EAX plus EDI. And we can move there our new character, for instance, character A. And of course, again, we need to specify that this would be a byte pointer, right? Just to keep everything clean. So what this do, the equivalent C code would be like bytes with this index EDI set equal character A. So this is another example of indirect memory operand, which is actually using a combination of 2 registers. So our x86 platform CPU allows this type of addressing with in indirect modes. Of course, using one register as address already puts us into indirect mode, but combination of the 2, of course, continues the same idea. So let's just quickly build this just to make sure that all the syntax is fine. Okay, so this is fine. And what else I would like to tell you? Well, so when you specify more than one register, the processor adds the contents of the 2 addresses together to determine the effective address, right? So we always say that when we execute this move instruction, we definitely want to go to the correct memory. Right here, there's like 5 bytes of memory allocated right here. So finally, we go to a single byte in this memory, and we need to know what is the address. And this address technically is called effective address. So let's just say that effective address is the address of the data to operate on, Okay, so this is an idea of the effective address. And so here, the effective address will be the result of combination of these two values. Of course, EAX contains address of bytes, and EDI is the index of the third element in this array. We compute the final address by simply adding these two numbers, and then we can store a new value, new character in that array element. So definitely a lot of things are going on here in this instruction, right? Let me just highlight this. So you can observe that we're specifying a byte pointer. Then we are also adding two registers. So of course we're using square brackets. So all this syntax. So what if we simply wanted to capture the address? Instead of doing all of this, just simply capture the address. So sometimes you don't want to instantly make this update, just store this character. The idea was that now you have EAX and EDI, and you want to remember, basically just load effective address into a single register and use it later, something like this. So what we can do is write an instruction like this: LEA, and let's use EAX, and say this, EAX plus EDI. Now notice that byte pointer specifier or operand right here is no longer needed. We're going to have to apply it later on whenever we use the EAX, which is the result of this. This is why it's important to think about it. LEA stands for load effective address. Load effective address also involves a computation. So you see that there is no way to do something like this with the move instruction. So with the move instruction, okay, move instruction cannot just take two registers and add them together. Move instruction is not capable of this. It's not flexible to like compute expressions like pluses or minuses. It can only take something and move somewhere else. But the load effective address computes the one of the possible memory operands, the possibility to compute the address expression at runtime, this time involving two registers, and stores it in the target register. So this is called load effective address. Right, so this is, let's just move, add comment right here. LEA is load effective address. Okay, so it's just, now notice another thing. What's interesting about load effective address instruction. It's, first of all, let's also build this just to make sure that all the syntax is correct. Everything is fine. So notice that I'm using square brackets right here. So it looks like from, our prior experiences, whenever we use square brackets, it kind of reminds us that we're actually accessing memory. But with load effective address, it never happens. Load effective address never attempts to access memory. It only computes the effective address. Again, effective address is the address of a data to operate on. So this is an instruction which is capable of doing some arithmetics with registers, and so you can actually use load effective address for general purpose computations, for whatever. You can look up the different formats of LEA, what it allows you to specify here. But my point right now is only this: with load effective address we can use square brackets, but this instruction never even attempts to go and verify that this address is valid. Okay, whatever is here and whatever is here will be added properly with respect to, like, the memory access rules and computation of the actual address, and the result will be stored in the register. So later on we can do the same thing here. right? But now we already have our EAX register, so basically I no longer want to use this comment. I'm just trying to show you that now we can use this effective address, which is perfectly computed by this stage. And of course, we have to repeat the specifier, what kind of data this address is pointing to. So this is a byte, and therefore we can store this byte in this memory. So these are some of the examples of indirect memory operands and what, how useful they can be, and in general, what is the idea behind this indirection, which makes our code very flexible compared to examples of direct operands.